To begin with, let's start by looking at IP addressing. I'm here in my Kali Linux instance, and if we go into our terminal, the Linux command that we can use to see our IP address is ifconfig. If we hit enter on that, you'll see that we have an iNet address listed here at 192.168.0.73. So this is actually our IP address for our interface. In this case, this is for Ethernet 0, our only physical interface on this Kali Linux instance. Below that, you'll also see that we have an interface called LO0, which is loopback 0. Now, if you've used Cisco routers, you're probably familiar with this concept. The loopback address is just a special virtual network interface that the device uses to communicate with itself. And that's mainly for diagnostic and troubleshooting purposes, but also that can be used to connect with some types of servers that may be running on the local machine. We also see that we have an iNet 6 address as well, which is IP version 6. So iNet is IPv4 in Linux, and iNet 6 is IPv6. So when I refer to IPv4 and IPv6, know that I'm specifically talking about the iNet and iNet 6 addresses that we see in this output. You'll notice that these are in very different formats. The IP version 4 address is in dotted decimal format, while the IPv6 address is actually in hexadecimal format. IPv4 addresses are going to be 32 bits long, whereas IP version 6 addresses are going to be 128 bits long. And that is how we communicate over layer 3. You're probably familiar with IP version 4 addresses that look like this. In my case, again, that actual address is 192.168.0.73. We also see something here called the net mask, or in other words, the subnet mask. This is going to determine which part of the IP address is the network address and which part is the host address. We need to know which portion represents the network on which the host resides. And we also need to know which portion represents the host itself. And so to understand this better, let's break down this actual address and net mask structure into binary. So here along the top of this table, we see our address in dotted decimal notation, and this is broken up into 4 different columns. These are called octets. So this address, this IP version 4 address, contains 4 octets. Everything separated by a decimal is its own octet, and we call this an octet because there are 8 bits making up the number inside of each octet. So if we look at these 4 octets, these numbers can also be represented by a binary equivalent using 8 bits in each octet, as we see in the second row. We'll get more into binary calculation in our subnetting section, so for now let's just look at how the binary IP address and subnet masks work together. So we see our IP address represented with the binary number shown here, and likewise we see the net mask or the subnet mask represented in binary as well. The subnet mask is going to be a series of contiguous 1s in binary, followed by a series of contiguous 0s. So anywhere that we have a 1 in the subnet mask, that means the corresponding IP address section is going to be considered the network portion. So in this case, we have 24 binary 1s, followed by 8 binary 0s. That adds up to 32 bits, as we said earlier. So in other words, the first 24 bits in this IP address are going to be the network bits, and the other 8 bits are going to be the host bits. So with the IP address on my Kali Linux host, we know that the network address, if we convert the binary back to dotted decimal, the network address is going to be 192.168.0.0. This also means that with this particular network, we can have host IP addresses ranging from 192.168.0.1 through 192.168.0.254. We can't start with 0.0, of course, because that is the network address. The largest decimal number that can be represented with an 8-bit binary number is 255. Again, we'll look closer at this when we explore subnetting. Now, you might be thinking, well, if we can represent 255 with an 8-bit binary number, why isn't 255 the highest host address that we can have? Well, if we jump back into my Kali Linux host, we're going to see the answer for this. We see some other information in here, and one of those listed at the end is the broadcast address. Notice that is 192.168.0.255. So that address is already taken as the broadcast address. So we cannot have a host with that IP address. The broadcast address is what we use to target all hosts on a network subnet. So if we send traffic to that address, it can be received by any other host on the same network. A quick way that we can calculate the broadcast address is to invert the subnet mask. So if we take our binary subnet mask and we flip every 1 to a 0 and every 0 to a 1, we get the following binary number. You see that's all zeros in the first 3 octets, followed by all ones in the last octet. We then take this binary number and we want to add that to the binary network address. Remember, the binary network address is 192.168.0.0. We see the binary equivalent of that here in this row. Once we add those together, you'll see the sum binary address that we have, and that does add up to the decimal equivalent of 192.168.0.255. That is our broadcast address. When we see IP addressing written out, we can see that in a couple of different formats. We might see that in what's called CIDR notation or prefix notation, where we write our IP address followed by a slash and then the number of binary ones in the subnet mask. In our case, we already said that we have 24 binary ones in our subnet mask, so we could write the IP address of this Kali Linux machine as 192.168.0.73/24. Or we could, of course, write out the full subnet mask in dotted decimal notation as well, as we see here. These concepts are essentially the same with IP version 6, but we do have a little bit different information. We still have an address, again, that is in hexadecimal format, but instead of a subnet mask, with IP version 6, we have what's called a prefix length. In this case, we see that the prefix length is listed at 64. So with IP version 6 being 128 bits, this means that we have 64 bits here for the network portion and 64 bits for the host portion. I'll also point out that you don't see a broadcast address listed for IP version 6, and that's because IPv6 doesn't support broadcast. It instead uses multicast addressing to different groups of devices. The big takeaway here is that with an IP address, we have some bits that represent the network and some bits that represent the host. IP version 4 is 32 bits, IP version 6 is 128 bits. The network bits come first, and the host bits are last. Our subnet mask is the piece that informs us which bits are going to be the network bits and which bits will be the host bits with IP version 4. That mechanism with IP version 6 is the prefix length. Let's also talk about private IP address classes. Now, there are actually 5 classes in total, but we're not going to concern ourselves with all of those. The 3 that we use most are Class A, Class B, and Class C. This is what we refer to as classful addressing because we're using an address class with a classful subnet mask. Let's start with Class A. With a Class A private IP address range, we have a network address range of 10.0.0.0 through 10.255.255.255. Next, you can see the network mask of 255.0.0.0, or in other words, a /8 subnet mask. This gives us the possibility of creating 126 different networks, with each of those networks being able to support over 16.5 million different IP addresses. A very large business might use this range if they have lots of endpoints. This is a small amount of individual networks compared to our other classes, but a huge amount of hosts. Class B ranges from 172.16.0.0 through 172.31.255.255. And that has a subnet mask of /16, or in other words, 255.255.0.0. Now here we have more networks, over 16,000, and just over 65,000 hosts per network. Finally, the range you're likely most familiar with, it's certainly the most common, is a Class C private IP address. This is 192.168.0.0 to 192.168.255.255. The subnet mask is a /24 mask, or in other words, 255.255.255.0. This is essentially the opposite of a Class A range. So with Class C, we have a large number of networks, over 2 million, and a very small number of hosts per network, only 254. Now, most of us in our own homes, we don't have over 254 devices connected to the network, so very commonly we see this in home settings. If you remember the Kali Linux IP address that we looked at previously in this video, that likewise was a Class C private IP address. We also have the concept of classless addressing as opposed to these classful schemes. This is where subnetting comes into play, which we'll explore in a future video. MAC addresses work at layer 2. When we talk about a layer 2 switch, such as the Cisco switch that we see here, this is going to make forwarding decisions based on the MAC address. And MAC stands for Media Access Control. We can think of this essentially as our physical address, in the same way that you might think of a physical street location address. This is a 48-bit address, and every device with a network interface card has a MAC address burned into the hardware by the vendor. This address is divided into two sections. The first section is known as the OUI, the Organizationally Unique Identifier. This identifier is given to the manufacturer by the IEEE, the Institute of Electrical and Electronics Engineers. The first 24 bits of the MAC address are the OUI, and this gives the vendor a block of possible MAC addresses for their devices. The last 24 bits are assigned by the vendor from this assigned range. There are vendors like maybe Linksys or Cisco who have multiple OUIs, particularly large vendors who have lots of products. There are actually several vendor search engines online where you can pop in the MAC address, and the IEEE registration is going to identify which vendor is associated with a particular OUI. That's very helpful if you're troubleshooting or performing diagnostics, or if you're pen testing. Let's say you see an unknown MAC address on the network, maybe from network logs or from a packet capture. This is at least one way that you can narrow down what type of device that may be associated with the network if you don't know exactly what that device might be. In fact, in our Kali Linux ifconfig output that we looked at previously, we also see below our IP addressing something called Ether. This is actually the Ethernet MAC address. What we see here is the 48-bit MAC address associated with the physical interface for this Kali Linux instance. Let's highlight only the MAC address portion of that. I'm going to copy that, and I'm going to open up a Firefox browser so that we can perform an OUI search here. Again, there are numerous sites where you can perform an OUI search. You can simply create a search for OUI lookup or OUI search. You'll see that one that I have used previously is this Wireshark OUI lookup tool. So if I scroll down, you can see some examples of how that works. You can paste in an entire list of OUIs, an entire list of MAC addresses, or descriptions. So I'm going to go down here and I'm going to paste this into place. And once I do that, I'm going to click the Find button. And you can see that at the bottom, we're told that our results are for VMware Inc. So this OUI is associated with the company VMware. Now, I have this particular instance of Kali Linux installed using VMware. So we are seeing the OUI for the physical interface being used with this virtual machine. You see the OUI is 00:0C:29. This is the OUI assigned to VMware as a vendor. The remaining portion of the MAC address that we see here is assigned from VMware out of their block of available MAC addresses. So in summary, MAC addresses work at layer 2, at the physical layer, and they are related to switching. Switches will actually build a MAC address table locally. As communication happens through the switch, it will learn about connected devices, and it will learn about their MAC address, and it will populate the local MAC address table in order to more efficiently forward traffic. These MAC addresses are some things that we might see during our pen testing techniques, so I wanted to show you how we could actually perform a search to figure out more intel about a particular device that we may not know exactly what it happens to be.